That's right.
Okay, so there, yeah, that's part of the physics. Alright, so, this is where we left off. Okay, so I got your text yesterday, I just didn't respond, I did post the video. Yeah, appreciate it. Okay.
So, is radioactivity useful or just wherever you are sitting, despite likely that there is a device nearby which contains a source of alpha particles?
So amusing.
Alright.
The source is radioactive americium.
So, everyone has a smoke detector at home. This is what's in it. Americium, let's see, he might have already said it.
95.
No.
You are totally safe from these alpha particles which cannot travel radioactive americium.
I didn't.
You are totally safe from these alpha particles which cannot travel more than a few.
So, what happens inside your smoke detectors, you have americium, I want to say 241. That's 243 over there. I want to say it's AM 241. That's in the smoke detector. And that's the brown ones here. And when they give off their alpha, they transmutate into 93, Neptunium. NP. So it'll, anyways, the point is when these americium atoms give off alpha particles, what happens is, I don't really have a lot of room for this, so I'll just kind of explain it. So you have a sensor, and then you have your americium over here emitting alpha. And the alpha hit the sensor. And when the alpha hits the sensor, everything's cool, the alarm doesn't go off. Well, alpha has really crappy penetrating power. What that means is, kind of like me trying to put the marker through my hand. It's not going to go through my hand very well because the marker's so big. Alpha particles are so big that air particles stop them, your clothes stop it. So alpha can't really penetrate very well through materials. So you have your sensor, you have your alpha particles hitting it. When does the alarm go off?
When there's not hitting it.
Right. So smoke comes in between, and the alpha particles hit the smoke. Smoke absorbs the alpha particles. Sensor doesn't get the alpha particles. The alarm goes off. That's how it works. Kind of cool. Now you know how a smoke detector works.
How does a battery make the?
You need the sensor. The sensor for the alarm. So these will give off radiation.
Turn the sensors on.
Yeah, yeah. So you need electricity for the sensor and the alarm, not the radioactive stuff. Good question.
So eventually the radioactive stuff would run out of particles that are emitting alpha particles, so you have to change it.
Yeah,
But it
I
would just
mean,
take a while.
I don't know the half-life of AM 241, but it's probably ridiculously long. And even when it goes through one half-life, you still have half of it left, so it still produces a decent amount of radiation. We can look it up, but yes, theoretically, when all this runs out, you got to get new smoke detectors. Not just batteries aren't going to do it. So anyways, the point of this is alpha has really, really low penetrating power. You need to write that down. What's up, Ben? Getting an apple?
Yeah.
Grab two. You need a good game tonight. 2 apples for Ben.
Thank you.
All right. Yeah, the alpha has the weakest penetrating power, meaning your clothes, pieces of paper can stop it. All right. So I always talk about if I have like an alpha gun and I'm shooting you guys, it would be kind of pointless because you could just hold up a piece of paper and block it. Okay.
What
So,
does it do to us? So
well, if it was to hit you, your clothes would absorb it. So it wouldn't, if you didn't have a shirt on, let's say, it would hit your skin would stop it.
then what would be the point of pulling up a piece of paper?
So it wouldn't hurt.
Well, so it wouldn't hit you. You don't want it's radiation. You don't want radiation on your body, even if it's only a weak
Even though it won't go
penetrating.
through us?
Yes, you still don't want to be exposed to radiation.
So
Yes.
So it's harmless. Kind of.
Yeah. Alpha is fairly harmless. Yeah. But these are not as harmless. Beta and positron will penetrate through your body. It'll go through your clothes, through your skin, but they will get stuck in your body. So they stay in your body. They don't go through. Gamma has the strongest, or maybe greatest is a better way. I don't know, whatever you want to write down. Strongest, greatest penetrating. Gamma will go right through us. So because it's so small, it's a wave, it can go right through us. Think of a needle. I can put a needle through my hand pretty easily because it's so small. But something big, I can't, right? So big particles, weak penetrating, small particles, strong. Question?
So is regular helium also technically radiation? So
Well, that's what they said in the video. It was just before this. Yeah, if you take a whole collection of alpha particles, you'll have helium gas.
okay, so it's like really bad when
But It's
like
a-
breathe helium.
It's a little different. Helium is neutral. Alpha particles have a positive charge, positive 2 charge. So I don't know the difference. The only difference I can think of is if this is coming from a nucleus, it's considered radiation. If it's just helium gas, that's not radiation.
And also, isn't that technically creating new matter? Emitting alpha particles?
No, because aren't you getting rid of that?
Well, but the nucleus is losing it.
Yeah.
So the nucleus is losing the mass, and that mass is
Forming
now.
a new particle.
All right. Well, you're very close. You're not creating matter. You're creating something else, even more dangerous. Energy. So mass is converted to energy. That's why the atomic bomb is so powerful and so dangerous. Not just the radiation, but the sheer power. And that you're making a good connection, but it's actually energy. Radiation is a form of energy, not just matter. It gets confusing. So all those laws, conservation of mass and energy, kind of throw them out the window at nuclear because you're changing the nucleus and it's creating energy. But theoretically, the mass on paper should be transferred to those products, like we did in the homework. You balance the numbers.
Yes.
In real life, it actually doesn't work that way. The mass of your products is actually a little bit less because some of the mass has been converted to energy. I was going to talk more about that on Monday. That's like a big concept with this unit, mass converted to energy. So that's a good point. One more question.
If gammas like go straight through, why is it dangerous? Because if you said, I remember you saying that there were like small enough ways that they would just go through the atoms.
But sometimes they hit them, and they can actually affect your DNA. They're so small, and that they're going to show that here. So I'll let him finish it, and then we'll go back.
Few centimeters in air. Beta particles penetrate much further through materials than alpha can. Radioactive atoms are used in medicine as tracers to show where chemicals travel in the patient. Beta particles are emitted and have enough energy to emerge from the.
So, anyone ever have a scan or know anyone who's had to ingest or get injected with a radioactive dye? Anybody?
I'm pretty sure my grandpa was.
You ever hear of a PET scan?
Yeah. Oh, is that the thing where you have to drink the shake before you?
Yeah, and then you have to wait for like 45 minutes or whatever it is. Yeah. So PET scans are, they might, Shane, stay with me. We need to go walk around, wake up. PET scans have lots of uses, but primarily to detect tumors, like cancerous tumors. So you drink this solution that's radioactive, and they tag the radioactive material with glucose, or the other way around. They take the glucose, tag it with the radioactive material. And tumors use a ton of glucose. What do tumors do?
Rapid cell growth.
Rapid cell growth. Well, to make cells, your body needs sugar. Sugar is the best form of energy. So a lot of glucose rushes to the area where there's tumors. And if there's radioactive tracers attached to it, it emits radiation, and then doctors can see it on a screen. So a PET scan stands for positron emission topography. So it's emitting positrons, and let's say there was a tumor here. This area on this person would be extremely bright. They call them bright spots. The brighter the spot, like the bigger the tumor or the more active the tumor is, and there's a lot of glucose being used. But if there's like a dull spot over here, that's probably not a tumor. So when you get a PET scan, you're looking at the very bright spots, and that's a really useful use of radioactive substances because we can figure out where tumors are from just that one scan. PET scans, when my stepfather had cancer, the PET scan was like what they always waited to see before they talk about, is the tumor shrinking, growing, has it spread? There's other things they can do, but PET scan was like the king. That's what they would look at. Yeah.
You're ingesting radiation, though.
Right. So that's another question. And after he, I think he was injected. I don't think he drank it, but because injecting it's a lot quicker for your blood, getting your the blood. But they gave him a piece of paper that explained how radioactive he was and how long he would be radioactive. So they said, don't go near newborns, don't go near people with compromised immune systems or really old people, because he was radioactive for like a day or a couple days. And it sounds crazy, but it's kind of like pros and cons. Now they have a good picture of where the tumors are, but you're radioactive. So I didn't want to stand next to him for a
could
while.
that change anything in his DNA though?
No, I mean it passes pretty quick, and the level, the intensity of the radiation is not that high. But would we wouldn't want it to stay radioactive for a long time. So these things have really short half-lives. So iodine, for example, that they're talking about, the half-life of one iodine sample I know is 8 days. Like the one he had was not. It was quicker, but good question. So that's stuff you do need to know. Could be on the test. Tyler, you with me?
Mm-hmm.
Okay. Moving on.
The body and be detected. There is a third type of nuclear radiation, gamma, which is not a particle at all. It is an electromagnetic wave, like microwaves or light, but it is actually 1,000 times more energetic.
Okay, couple things here. That doesn't happen.
So it doesn't come out of like.
Right, it doesn't come out of the microwave. I get it for the example, what they're showing, but it doesn't come out of your microwave. If you look at the glass on your microwave, what do you see?
Blinds.
Yeah, it should be like a mesh type thing. Yeah, it's because microwaves can't get through that. I still don't recommend, Shane, don't like smush your face up against it and watch what's heating, alright? Don't do that. I don't recommend holding your head in front of it, but I think that's kind of like an old wives' tale. I don't
Put foil
think
into
really.
it.
What?
Put foil.
Don't put foil in it. Now, did it look like this was moving faster?
No. Yes.
No, it's just going up and down
Didn't it say?
Or light, but it is actually 1,000 times more energetic.
Does it look like it's moving faster?
Yes.
Yeah. Well, it can't, so that's kind of, I have a problem with that a little bit. It's impossible. All light moves at the same speed. This is light, visible light. This is microwaves. This is gamma,
That's why I
light.
said no.
All light moves at the same speed, which is
Light speed.
the speed of light. Right.
Well,
3
why-
times 10 to the 8th meters per second.
Why did you say that it was?
It's more
1,000 times?
energetic.
Okay.
So there's more energy associated with it because the peaks are very close together. It's a high frequency. So it's more energetic, leave it at that. But it's not moving from point A to point B faster. There's just more peaks from point A to point B than, let's say, microwaves. That's what that means. Okay.
Invisible light. Gamma rays may pass right through your body. Gamma is used to zap the bacteria in fruit
That's called
to increase its shelf
irradiation.
life, or in radiotherapy to kill cancer cells.
So, long time ago, my dad had cancer. He went through radiation therapy. They used cobalt-60. That's cobalt-59 over there. Cobalt-60 emits gamma, and at St. Peter's, they do this. And I remember back when he was getting radiation therapy, they actually put like a semi-permanent tattoo on him, and it had like crosshairs, like you would see like in a scope or something. And that's what they would line the machine up with, and then they would blast the tumor with radiation. So it's kind of interesting. Radiation causes cancer, but it can kill tumors. So that's radiation therapy. Again, something you've probably heard of. You know, everyone knows somebody that had cancer, has had, whatever. But that's radiation therapy, and again, it's from taking radioactive samples and just focusing the radiation on the tumor. So that's another medicinal use.
Radioactive substances get hot, and this heat can be used to generate power. This heat has been put to use in space probes and, in the past, in pacemakers for hearts. The more abruptly nuclear radiation is slowed down, the more damage it does to the atoms it hits. This is called ionization. Alpha causes the most ionization as it crashes into other atoms,
So there you
and
go.
gamma the least.
So gamma's bad for us because it goes through our body, but alpha causes more ionization. You don't need to know that, so don't worry about that. But it's all bad. Radiation's just straight up bad. Jake, you with me? Pick your head up.
For humans, the most serious effect of radiation is the damage that it can cause to our DNA. Although alpha cannot penetrate your skin, if you inhale or ingest a radioactive nucleus, the health consequences can be severe. Radioactivity is both useful and deadly.
Okay, lights please. Now before we go back, I want to get one example of artificial transmutation in our notes. Artificial transmutation, and then we'll go back. Alright, so this is when scientists, I'll say force, and an isotope to become radioactive, which is transmutate, by, the word is bombarding the nucleus with smaller particles, like a neutron. Think of bowling. The bowling ball is the neutron. The pins are the nucleus of an isotope. You take the bowling ball, chuck it down the lane. If you throw it hard enough and accurate enough, it hits the pins. Whiz it down the bowling lane. All right, the pins explode, bounce all over the place. Okay, I'm not talking about the slow roller where the pins just kind of fall over. That's not what I'm talking about. I'm talking about, you get it down there with some speed, velocity, and they kind of blow up. That's exactly what this is. That's called artificial transmutation. So, just to get an example, let's take aluminum. We'll take aluminum 29 over 13. We're going to hit it with a neutron. And in the process here, go ahead, I'll let you get that down. So again, this happens in particle accelerators. Will's favorite hadron collider. Take a neutron, slam it in the nucleus of aluminum. When it does that, something's going to happen. Okay, the nucleus might split apart. It might just release tons of energy. It might release radiation. It might turn into something new. Transmutation. But that's what this is. I'm only going to give you this one example. We're going to talk about 2 other examples on Monday. Does anyone know what other 2 artificial reactions we do? One of them we try and make energy with. Nuclear.
All of those were.
Well, no. There's a specific reaction type we use in nuclear reactors to make electricity. That's what an F.
Fission.
Fission, nuclear fission. Right. There's nuclear fusion too. We'll talk more about that Monday. But anyways, you hit this with a neutron. All right, and then you create here. I want you to fill in the blank. It's going to be 30 over 12 mg. 30 over 12 mg. You guys fill in the blank.
Wait, has it 30 over 12? 13 plus 0 equals 13.
Yep. Very good.
Then why?
You got to fill in the blank.
Oh, oops.
Fill in the blank. So this is, again, just like your homework. And why is this artificial? There's 2 reactants. Okay, we're taking a neutron, slamming it into the nucleus of aluminum. That's something we are doing, humans are doing it, scientists are doing it. Okay, nature doesn't just take neutrons, start pitching them at aluminum. That doesn't happen. What's the blank? High heels. Yep, 0 plus 1e. Shane, you with me?
Yeah.
Jake, you with me? Everybody's looking a little tired today. 1 plus 29
Oh, okay.
is 30, so this needs to be a 0.
Yep.
You with me?
Yep.
Okay. All right, let's go back.